Okay, let's get things started. Can you all hear me from this microphone? It's not coming out the speakers? It is coming out the speaker? No, you can just hear my voice. All right. Is this microphone coming out the speakers? Okay, let's get rid of this one. Okay, so today we're going to talk about how to prove various types of statements. And in the process, we'll look at some first properties of groups. So I'm going to kind of go through different types of structures that mathematical statements take on and show you how to approach proving those different kinds of statements. And I'll try to give examples either of proofs that we've done already or new examples involving these first properties of groups along the way. So just to start things off, for the purposes of this discussion, a statement is just a reasonably, so a statement is a reasonably grammatical and unambiguous sentence that is either true or false. And in the case that we have a statement that is true or we believe to be true, we usually want to write a proof of that statement. So proof of a statement P is a series of steps which are themselves statements that establish beyond doubt that the statement P is true under all circumstances. Okay, and then just as a sort of notation, typically at the start of a proof, you'll see, where is he? Hey, P. No. So typically at the start of a proof, you'll see something like this, and then, okay, hey. And then you'll see the content of the proof written, and then at the end of the proof, there is like a little square. And I more or less follow this format in lecture, but also in like written mathematical documents. You see this, and the proof is just like, or the square is just there to sort of like let the reader know that the proof is over, and then whatever follows that is like further discussion that moves on to like a different topic. Yeah. Yeah, so in LaTeX you can write begin proof, and then write the content of your proof, and then end proof. And then that will produce this kind of environment. And I don't think that this comes automatically in LaTeX. I think it's in like one of the packages that you typically add, like AMS Math or something like that. But I forget exactly what package, but this is in, and you need to use some package that I don't remember. Are there other questions? Okay, so let's go through some different types of statements and discuss how to prove them. So one of the most common types of statements is something like if P then Q. And this is the same, so this is like equivalent to P implies Q. So if you want to do this, there's sort of two methods of proof that you can sort of use. So the first one is to assume that P holds, and then from that assumption prove Q. So that's sort of like the more straightforward method, but there's another way that you can do this, and that's called the contrapositive. And to do this method, you would suppose that Q is false. And from that assumption, then you would prove that P is also false. So these two things are logically equivalent, and either of them suffices to prove a statement of the form if P then Q. So let's see an example of this, and this will be a property of groups. And this is called the cancellation law. So this says let's let G be a group. And we'll let A, B, and C be elements of the group G. Then here's our statement that we want to prove. It says that if BA is equal to CA, then B is equal to C. Okay, so this is the statement that we would like to prove. So let's provide a proof of this using the sort of just the axioms of groups that we saw on Monday. So the structure of our proof, we're going to assume that we have elements A, B, and C from the group G, and suppose that this holds. And then what we want to prove is that we also then have this conclusion. So we'll assume A, B, and C are elements of G such that BA is equal to CA. Okay, so then just thinking about the properties of groups that we have, we know that A has an inverse. So we'll let A prime be the inverse of A. So then multiplying this equation on both sides on the right by A prime gives us the following. So we have BA times A prime is equal to CA times A prime. And then we can use the associativity law to change up the order of multiplication. So this is by associativity. And then we also know that A times its inverse is the identity in the group. So this is going to turn into B times E is equal to C times E, where E is the identity. And then since E is the identity, we then can conclude that B is equal to C. And this is what we wanted to prove. So the proof is complete. Yeah?
Do we have to do the whole associativity thing every proof, or just jump straight to the proof?
Yeah, I think, after, we have these, basic examples where we're, proving things from first principles, right? So in that context, I think, mention associativity, but, as we go on in the course, this is, a property that we're familiar with, and we're, comfortable just, redoing the order of multiplication. So, yeah, I think most of the time we don't need to, go into this level of, of detail. Yeah. Other questions? Okay, so that was the group cancellation law and if-then statements. So now we'll talk about and statements. This is the second type of mathematical statement that arises. So this is something of the form, so if we have a statement P, we want to show that P and Q is true. So to do this, you would just need to prove P is true, and then follow that up by proving that Q is true. So you have to prove each statement individually. And we have sort of seen an example of this. So last week we proved the statement that if tilde is an equivalence relation, on a set S, then the equivalence classes of tilde are a partition of S. But this, the second half of this sentence, so that these things are a partition of S, this breaks up into sort of three different conditions. So to prove that something is a partition of S, we need to prove that the equivalence classes cover S, and that the equivalence classes are disjoint, and that the equivalence classes are non-empty. So if you go back and think about how we proved this statement, we started off, so this is an if-then statement with an and statement as the conclusion. So we started by assuming the first part of this. So we assumed that tilde was an equivalence relation on the set S. And then we proved individually that then the equivalence classes cover S. We proved that the equivalence classes were disjoint. And we also proved that the equivalence classes were non-empty. So that's an example of proving an and statement. Other questions? Okay, so now I'll talk about or statements. So if we want to prove something of the form P or Q, then a way that we could prove this is to suppose that P is false and then prove Q. Okay, and that's sufficient to prove P or Q because in the scenario where P is then true, P or Q also holds automatically. And it also suffices to show, you could switch this up if for some reason it's easier to assume that Q is false and then prove P. So you could do this the other way also, so or vice versa. Okay, so I'm going to do an example of this. Bean. No. And this is called Euclid's lemma. So this says that if P is a prime that divides AB, then P divides A, or P divides B. Okay, so that's the statement of Euclid's lemma, and let's break this statement down. So the sort of largest structure that I see is an if-then. So I have if this condition holds, then I have something else. So I'm going to start by assuming this part, and then we need to prove this part. And then now that we know that we've broken this down and we know we need to prove this, we see that this is an or statement. So I'll assume that this does not hold and then prove this part. So here's how the proof will go. So we'll assume P is prime and P divides A times B. And then we'll also assume P does not divide A. So then what we want to prove now, it suffices to show that P divides B, and then we'll be done with the proof. Okay, so if P does not divide A, so since P does not divide A, we know that the GCD of P and A, so the greatest common divisor of this in particular is going to be a divisor of P, and P only has two divisors. It has itself and 1, and since P does not divide A, that means that the only thing that the GCD could be is 1. Then we know that there exists S and T such that 1 is equal to SP plus T times A. Okay, so we can write 1 as a linear combination of P and A. Now I'm going to just multiply both sides of this equation by B. So we have that B is equal to P SB plus AB T. Okay, and now notice P divides PSB plus ABT because P clearly divides this summand, and then P also divides AB. So that implies that P divides B, which is what we needed to show. So that concludes the proof. Are there questions about this? Okay, so other types of statements that you might encounter. We also have if and only if. So something like P if and only if Q. Whoop. And this is sometimes abbreviated as P if with two F's Q, or with arrows. Sometimes people write something like this, P if and only if Q. So the way that you'd prove this is you need to just show both implications. So you need to show P implies Q, and then separately you need to show Q implies P. I didn't write down an example of this, and I don't know if we've already done one, but we'll see this come up plenty often. Actually, I think there's one on the homework this week. So you'll get practice with this. Okay, so this isn't a type of statement, but rather just like a different proof method. So this is proof by contradiction. So say we want to prove any statement P, then the way that this proof method works is to assume the statement not P. So assume that the negation of P is true, and then show that this leads to something that is clearly false or nonsensical. And this is called the contradiction. And we have seen an example of this already. Oops. So if you want to go back and look at one that you've seen, when we did the proof of the first principle of mathematical induction, we had a couple of cases, and we showed that one of the cases was impossible by contradiction. So one of the cases was done by contradiction. Okay, so then the next two types of statements deal with quantifiers. Are there any questions about proof by contradiction? Yeah.
It's just kind of like when we're doing homeworks, basically, and if we try to prove by contradiction, we get to the contradiction, is like how you want us to just want to say and therefore P at the end of it. Like we assume
Yeah. Okay, so how to structure a proof by contradiction. So at the beginning of your proof, you might write, for contradiction, assume, and then write down whatever not P is. And then you'd have like the content of your proof, and then at the end you conclude that 1 is equal to 2, and then you could write something like, this is a contradiction. Therefore, P holds, or something like that. And then like end of proof. Okay, me. No. You're bad. Okay, come here. Are there other questions? No. Okay. So next I'm going to talk about quantifiers. So this is like statements involving things like for all, let's say A in A, the property P of A holds. So to prove such a statement, you would just let A in A be arbitrary, so just any element of the set. And then you must show that P of A, whatever that property is true. So an example that we've seen is, so say you want to prove that a function is surjective. So let's say we have some function from a set A to a set B. And we want to show that this is surjective. So what does surjective actually mean? So this means that for all little b in B, we have the property that there exists A in A with f of A equal to B. Okay, so to prove that a function is surjective, then what we would need to do is let B be any element of B, and then show the second half of this, so show that there exists A in A with f of A equal to B. Okay, and this is leading into the sort of other type of quantifier statement that you might encounter. So the other one is statements of the form there exists. So there exists A in A with property P of A. So the way that you prove statements like this typically is to find or construct some specimen A satisfying P of A. So in the surjective function example, So if we wanted to show that this function f was surjective, then like the second half of this is that we need to show that there exists an a in A such that the function f maps A to B. So then what we would need to do is find the little a such that f of A is equal to B. And sometimes you appeal to a theorem or an assumption that there exists something. So, for example, at the, was it on Friday that we talked about surjective functions? So we proved that the composition of two surjective functions is also surjective. And in that proof, we appealed to the fact that individually the two functions were surjective, right? So that provided us with the A that was necessary to get the correct output. So in that case, I would call the proof like non-constructive, because it doesn't actually tell you like exactly how to construct the element A. So yeah, sometimes these proofs really involve like constructing the exact thing that satisfies what you need, and sometimes it appeals to like something else to just guarantee that it exists. Are there questions about quantifiers? Okay, so the last type of statement that I wanted to talk about was things like, so we'll just call this one uniqueness. So to prove something like the element A in A with property P is unique. So there's only one element of A with that property. The way that you would prove this is that you would assume that there's some element so that there's some A prime in A which also has the property P. So you would make this assumption and then show from that that A and A prime are actually equal. So then you would need to show A is equal to A prime. So this is how you prove that things are unique typically. So let's do an example, and this will be another like a property of groups example. So this is called uniqueness of identity. So this says in a group G, there is a unique identity element. I'm going to give you a few minutes to think about and discuss how to prove this statement, and then we'll go through the proof together. Okay, so let's go ahead and prove this. So to start off, we'll assume that E and E prime are both identities in a group G. So then what we know from that is that for all A in G, we have the following two things. So we know that A times E is equal to A, and we also know that E prime times A is equal to A, since E and E prime are identities. And then in this left equation, we'll substitute in we'll sub in A for E prime, and then in this one we'll substitute A goes to E. So what we get out of this, So what we get out of this is that E prime times E is equal to E prime, and E prime times E is equal to E. Okay, so from these two equalities, we can then conclude that E is equal to E prime, and the proof is complete. Okay, are there any questions about this one? Yeah. Okay, yeah, so we know that this equation is true for any element A in the group G. So in particular, it's also true for the element E prime. Yeah. And then same for this equation. Yeah, are there other questions? Okay, let's do another kind of similar one. And also, by the way, now that we've proved these things, you can assume this is true for any group, so you can use this fact as you wish. Okay, so then the second theorem. So this is uniqueness of inverses. Okay, so this says that we'll let G be a group. Then for any A in G, the inverse of A is unique. Okay, so any element has just one inverse, and we'll prove this as follows. So, similar to the last proof, we'll just suppose B and C are inverses of A. So we'll assume that they're both inverses of A, and then we want to show that B and C are equal. So the fact that, then the fact that B is an inverse of A tells me that A times B is equal to the identity E, and A times C is equal to the identity E. So where E is the identity. And right, it's the unique identity. So we're not, when we do these two multiplications, we're not getting different identities because we know that the identity is unique. So we can conclude that A times B is equal to A times C. And then earlier in lecture, we proved a cancellation law. I think we proved a right cancellation law, but you can use the same proof to show that there's also a left cancellation. Did we prove? I'm just going to go back and look. Yeah, okay, so we proved like you can cancel on the right, but you could use this exact same proof to show that you can cancel on the left as well. So, so we'll apply that cancellation law. Then we can conclude that B is equal to C by left cancellation law. Okay, so that completes that proof. And then okay, so let me just make a notation note. So now that we know that inverses are unique, we'll denote the inverse of an element A by A to the minus 1. And then this is like in a group where the operation is multiplication, but if the operation was addition, we might write minus A if the operation is addition. Are there any questions about this? Let me make another note about cancellation laws. So we know that AB equals AC implies B is equal to C, and we also know now that BA equals CA implies B equals C. But if you have AB equals, so let me write this out more fully. If AB equals CA implies B is equal to C, then for all, let's say, for all A, B, and C, then your group is actually abelian. So obviously, if the group is abelian, you could, commute these two elements and then do the right cancellation law. But if you actually have this property for all elements A, B, and C, that's equivalent to G being abelian. So in general, you can't cancel in situations like this because the elements of your group may not commute. Okay, so that's all I have for you for today. And on Friday, we're going to talk about something called the order of a group, and we're also going to talk about subgroups. B. Yeah, that's fine. It's probably not like ideal because like then you know if you have questions it's harder to get through and stuff. But yeah, that's fine. Bean. Why you do this? No. Hi. How's it going? Let me see. Yeah, because I think homework 2 is just about chapter 2. Yes. Yes. Yeah.
Okay, so for this one, I was looking at it, and like, in for the first, like for the property that's like, if you multiply two of these elements, you get another element in the group.
Mhm.
Like, what's a better way than just like trying every single combination of two numbers?
So, here's what I'd suggest, which actually isn't like better than that. I would suggest just writing out the multiplication table for this group. So you will have to do that whole multiplication.
Right.
But then once you have the multiplication table, you'll be able to just like observe all of the properties by looking at the table.
Oh, alright.
So you will have to like, but like obviously for multiplication you have to do all of these
Yeah.
multiplications. But you can use it.
Yeah.
Have a good class.
Thank you so much. Have a good rest of your day.